Good morning. Let's start our lecture. So we'll continue on a differential equation of first order, right? In the last lecture, we talked about two different kind of a technique. The first kind of technique is separating variable, which is used on homogeneous first order differential equation, which is pretty simple. And the second technique is integrating factor methods, and that one is applied to non-homogeneous linear ODE of this type. Okay, so this is non-homogeneous. Okay, and this is a linear ODE. Okay, because if you compare this one to the standard format, it's linear. So the objective, as he said, is we're trying to find a suitable integrating factor sigma of x, so that when you multiply the sigma x to the left side and then both the right side here and the left side, right? So you multiply this sigma to the left side, then the left side can be rewritten into this format here, okay? Into this format. So if we can do that, then basically we can integrate. We can integrate this differential equation now, okay? So that means this d over dx sigma y will be equal to sigma qx like this, right? Yeah. And then we can integrate. And then we can integrate both sides. Okay? Can integrate both sides. So that's the idea of the integrating factor methods. So the objective is you're trying to find a suitable integrating factor, right? So what would be the sigma at here? So we went over some steps here. Basically, you use product rule to expand this term right here, right? And solve for the sigma. So we can find that our sigma, right, is this. Okay. This is our sigma here. So but this is the integrating factor methods. Okay. Yeah, this is the integrating factor. Now we'll go over some examples here, right? And I don't want you to, and it's not necessary to memorize the formulas. Okay, it's not necessary because this is the procedure here. Once you go over a few examples, you'll see that it's quite simple. So you can always starting from scratch for every examples, right? Yeah. So using formulas in the midterm, I'm not going to give formulas, but if you remember formulas wrong, right, and you won't have right results, right? And but if you go through steps, you're still going to be fine. So let's solve this one here. xy prime plus 2y equal ln x over x squared plus 2 and x greater than 0. Okay. So this is the first example here. Okay, so when we do when we look at this example here, okay, I want you to be careful is this. Because all of these things that we were talking about is talking about this with respect to this standard format here, right? Standard format. So, but the standard format means you look at this one here. The coefficient in front of this first derivative y prime here is what? Is 1, right? So, which means you look at this one here. This is x. This is not 1. So, the first step here, what we need to do is to normalize this differential equation. Okay. So, basically, before you apply all the techniques that are here, see, this is the danger of applying the formula, you know what I'm saying, right? If you directly jump into this formula, this differential equation, trying to apply the formula, and chances are you're going to end up with the wrong results, right? Okay, so first step, just wash it and convert it and normalize it, okay? Or just see a convert to standard form. Okay. So that basically means divide x, okay, by both sides. Okay. So that'll give us what? Y prime plus 2 over x, y plus ln x over x cubed plus 2 over x. So that becomes this, right? Okay. So now we're ready to apply the standard approach of this integrating factor methods, right? So let's take a look at how do we. I'm not going to apply the formula. I'm going to go over this procedures here, right? Yeah, I'll go over those procedures. So what we do is, and then this is step number 2 now, the big steps. Okay. So we multiply sigma x. Okay. So we end up with sigma y prime plus 2 over x y equal sigma and sigma here. Ln x over x cubed plus 2 over x sigma here. Okay, so that's, you multiply the sigma, the integrating factors we're trying to find it, of course. You multiply the integrating factor to both sides with this differential equation. Okay, yeah. Okay, so now the objective is to write this side here. The objective to write this side into this. Okay, into this. Right, the objective is this. And in order to do that, okay, in order to do this, in the last lecture, you can also try this out. So basically, when you write this one into this side here, this equation using product rule is sigma y prime plus sigma prime y, right? Sigma prime y, product rule. Okay. So you want to write this one into this one, and it happened that this term and this term are the same. So this term has to be the same as this term. And there are 2 y's, so only end up with this equal to this, right? Yeah. So that's basically a general thing here. If I write it over here, okay. So in order to do that, right, and we have to have sigma prime equal to sigma p. Okay. So that's basically this step here, right? If I look at this one here, say sigma prime has to equal to what? Sigma multiplied by this, right? Okay. Sigma prime has to be the same as this. So that gives us, okay, sigma prime equal to sigma multiplied by 2 over x. Okay. So if you want to jump steps, you can jump a step, one step here. How do I find a sigma? Sigma has to satisfy this equation here. Okay, sigma prime equal to sigma multiplied by px. Okay. There's one little trap here is this. What is the px? Px is the coefficient in front of this y here, right? Okay. Now remember px is a coefficient. If there's a negative sign here, is something minus something here? What's the px? Px is not just coefficient, including that what? Negative sign, right? Yeah, I've seen many of that kind of mistakes. Because you don't have the negative sign, and basically you're going to miss a negative sign here, right? If there's a negative sign there, and you're going to end up absolutely total different results from here. So for each example, sigma prime equal to this, and we're going to solve for sigma. And this is equivalent to saying d sigma over dx equal to sigma 2 over x, right? And this is equivalent to saying separating variable. So d sigma, put the sigma all together, put the x all together. Okay, yeah. So that's this step here, right? Separating variable. separating, yeah. Okay, so then integrate both sides. Okay, integrate both sides. So this side here is integration with respect to sigma. The other side there is integration with respect to x. And so that gives us ln sigma equal to 2 ln x, right? 2 ln x. The question itself specifically said x is greater than 0, so you don't have to put a negative sign. You don't have to put an absolute sign in here. Okay? Yeah. So then solve for the sigma. Then what's the sigma here? Right? Yeah. Sigma equal to x squared. That's right. Right? So basically, this side here is equal to ln x squared. Then you take exponential of both sides, right? Exponential both sides, you get the sigma equal to x squared. Okay, any questions? Yeah. So get all the details, all the steps. There are little details sometimes. Okay, get all the details clear. Okay, so maybe some of you ask is, why don't you plus a constant c at here, right? Yeah. As we said, we don't need a general solution for sigma. We need what? We need one, right? We need one solution. Okay. So you can choose a +2 or +3, whatever you want to put it here. But ultimately, you only need one. Okay. So that's why we don't need a plus constant here. Okay. Okay. So now once we get a sigma now, okay, and that sigma will satisfy this equation to write that into this format. Okay. So then what we're solving now, we are basically solving, okay, d over dx sigma y equal to sigma multiplied by, right, the big right side, which is this guy here. Okay. So ln x over, whoa, oh, what happened here? Yeah, good, okay. X cubed plus 2 over x, right? Yeah. Okay, so this is basically solving the original one turning into solving this one here, okay? So there's one common mistake is some students forgot to multiply the sigma at this right side here, right? Yeah, don't forget that. And our sigma is x squared, okay? So we can do x squared, multiply this into first. Okay. So that's ln x over x plus 2 over 2x, right? That's 2x. Okay. Yeah. And now we're ready to separate the variable and integrate. So multiply dx to this side here, right? Multiply dx over here. So we have a d sigma y equal to ln x over x plus 2x dx. Okay, dx. And now you integrate. Okay. Now you integrate. So this side is simple, just sigma y. And this side here, the integration, okay, you need a little bit observation in here. So there are two terms, integrate separately. So I guess the trick maybe is the first term. Okay. So first term. And what will be this one here? What technique would you use? Quotient rule? Substitution, that's right. I'll show you my way here always, basically this is equal to what? Ln x and d ln x, right? So substitution, if you do it, you let u equal to ln x, right? Yeah. And but I'm using substitution too, but it's just a different way of doing it. And the second one here, 2x, that's just basically x squared, right? X squared. And here, d ln x is 1 over x, so it's basically this term here. And the ln x is the same thing. So that's going to be 1/2 ln x squared, right? Ln x squared. So this, you can treat this as one single quantity, ln x, right? One single quantity. And plus x squared. Okay. Now this is the time you can plus a constant c here. Okay. Now this one you need a constant c. Okay. Yeah. Because you need the constant c to solve for initial values, right? Okay. So we basically solved the question. Sigma x equal to this whole bunch here, and sigma equal to x squared. So just basically divide the x squared by both sides, and you get a solution for the y, right? For solution y. Okay, so that y will equal to 1 over 2x squared ln x squared plus 1 plus c over x squared. Okay, yeah. That's a solution. Okay. So when you practice, okay, in your assignments, okay, I want you to follow through all the steps here. Okay, don't try to remember any formulas. When you try to follow the steps here, you're basically understanding all the integrating factor methods perfectly, right? Yeah. If you use a formula, I'm pretty sure there's somehow you're still wondering where's that from, right? Yeah. Any questions? All good? All right. Okay. So any type of equations, right? They're basically all the same approach. Okay, all the same approach here. Okay. So let's take a look at another one in here. Okay, let's take a look at initial value problems. Okay, initial value problem. So when we solve initial value problem, first of all, what I'm showing you here is the general approach, and then I want you to solve, okay? And then if we got time, I'll show you another type, okay? But generally, we're not going to follow that steps. Okay. So here's the differential equation with an initial condition.
Is that 4t right there?
This one? Yeah.
Right
1 plus t squared.
oh, back one. Right there.
4t, yeah. All right, so let's see how do we solve this one here. So we're still gonna use our general approach here, okay? Step number 1, normalize it, right? Convert it into the standard format, okay? So the reason is because the coefficient here is not 1, right? So divide the 1 plus t squared by both sides. Okay, so then this is 1 plus t squared to the power negative 2. So you divided another one, and it's actually 1 over 1 plus t squared to the power 3 now, right? Okay, so that's this one here. Step number 2, okay, so we're trying to use integrating factor methods, okay. Now the reason because this is a linear ODE, okay, yeah. So multiply a sigma on both sides of this equation. Okay. And we're trying to rewrite the left side into sigma y bracket prime format. Okay, right? We're trying to write it into this. In order to do that, our sigma has to satisfy this equation, sigma prime equal this guy here. Okay, so sigma 4t plus 1t squared. Okay. So when you follow the steps here, basically every time you look at the pattern, right? It's all the same pattern. You know, this sigma prime has to be the same as sigma multiplied by this. Okay. Now, when a student asks is, when you write a sigma, you didn't write sigma bracket something here, right? Yeah, I'm kind of neglecting there, but you need to be clear what kind of function this sigma is, right? You know, basically you look at the differential equation. This is t here is your dependent variable, right? So sigma in this question here must be a function of a t, okay? And if you want to if you want to write a sigma instead of just a sigma, but a sigma bracket of t, that's absolutely fine. Okay, yeah. Okay, so then over here we have we can separate the variables. Okay, so that's d sigma over sigma equal to 4t plus 1t squared and dt. Right, dt. So here comes another integral. Okay, integral of these two. Okay. So what technique would you use for this one here? Look at this one. Substitution again. Yes. Yeah. Substitution. Okay. So if I do it my way here, and I have so I have what? I have this is a 4t dt over 1t squared. Instead of t dt here, I'm going to write it as a t t squared. Okay, dt squared. dt squared is dt squared equal to 2t dt, right? 2t dt. So I got another 4 here, so I just put a 2 in here, right? So 2 by 2 is the 4, it's the original 4. And I have 1 plus t at the bottom here, right? So I will just plus 1 in here because d, a constant, is always 0. So d bracket 1 plus t squared is basically 2t dt, right? It's basically 2t dt. So that equal to this one. Okay. So if you're I'm just doing my way here, kind of quick. If you're not comfortable with this one here, what would you do? You let u equal to 1 plus t squared, right? And then you do your regular approach of substitutions. Okay? Yeah, same thing. Is that clear? Okay. So this one equal to 2 ln 1 plus t squared, right? You don't need absolute sign because this is 1 plus t squared is guaranteed to be greater than 0, right? Yeah. Okay. All right. So sigma, this side here is ln sigma. Okay. So ln sigma equal to this. So that means the sigma equal to 1 plus t squared. Okay, excellent. Okay, so now I'm ready to go back to this one here, right? Once I found my sigma, I'm ready to come back here. To come back here meaning solve what? Solve sigma y prime equal to this. Okay, to solve this. So then I have sigma y prime, which is d sigma over dt equal sigma. In this case, I solve sigma, so I'll use my sigma right here. Multiply by which term? Multiply by this term. Okay, what about this term? All right, so this term cancel 1, so cancel 2, which is 1 plus t squared, right? Plus t squared. Okay, separate the variable now. Move the dt to this side here. So d sigma y equal to 1 over this dt. Okay, and integrate. Okay, integrate. Okay. Yeah. So this side is just simply sigma y. And what's the integral of this side here? 10. 10 or 10 inverse? 10 inverse, right? Plus a c. Yeah, in the 248 we had some partial derivative of such kind of arctan functions, right? Yeah. All right, so then solve for y, divide this sigma by both sides. So we end up with 10 inverse t, and sigma is this. Okay, c over 1 plus t squared. There we go. That's the solution for the y, right? Solution for y. And we were given an initial condition. So we can apply the initial condition to solve for the constant c. Okay? Yeah. Initial condition is y of 0 equal to 1. Okay? So initial condition is y of 0 equal to 1. Then what do we do is, right from here, you let t equal to 0. Okay, you let t equal to 0 basically. So we get y of 0. When we let t equal to 0, let's look at what's the solution for the y, right? Let t equal to 0. T equal to 0 meaning this denominator here is 1. And what's the arctan of 0? What does arctan of 0 give us?
0.
0, right? And yeah, so this whole term is 0. And this is just a c, right? It's just a c here. And then initial condition tell us y of 0 is 1, so that equal to 1. So basically means c equal to 1. Okay, c equal to 1. Just a second here. Is that am I right? Yeah, I think that's right. No. What is the value of a tan? Hang on a second here. Yes. Okay. There's a little mistake in my lecture notes. Yeah. Any questions? Okay. So this is basically a general approach to solving initial value problem here. Okay, initial value problem. So I'll give you another simple idea of solving initial value problem, right? Yeah. So we'll take a look at this one here, right? We'll take a look at this approach. But I need you to know this approach here, initial value problem. Okay. Okay. So I'll give you a circuit here. This is the RC circuit that we have used in previous lecture. Okay, this is the RC circuit here. Okay. So we have derived the equation of motion for this one here. We're looking for is the output voltage across the capacitor. Okay, output voltage across the capacitor. The governing equation for this output voltage across the capacitor is this one. Okay, this is a governing equation. You use the KCL law, and you'll be able to do end up at this differential equation. Okay, yeah. I think you probably have done some experiments. For example, you'd use RC circuit, and this side here connects to a signal generator, right? And you measure the voltage output across the capacitor, right? Look at the time histories of the voltage across capacitor. Okay. Have you done that kind of experiment? Yeah, right? So if you recall that, what does it look like when you put it into a square wave? Right, when you put in a square wave, what does it look like? It's kind of like goes like this, that, right? Yeah. So see, the question is why it goes like that, feels like this, isn't it, right? Yeah. So this is basically how you can solve this analytically. Okay. So you see, when you putting a square wave into it, as a matter of fact, if I only look at this portion here, right? What is that? Basically, what kind of input did I put in? Unit step input, right? Well, it's not unit step, but I guess it's 5 volts or whatever. But it's an amplitude multiplied by unit step input, right? Yeah. And the response here, remember what we call it? It's called unit step response, right? Unit step response, okay? Yeah. But I'm going to derive a general. Basically, I'll leave this Vs as it is, okay? Leave this as it is, and let's see what kind of response the system have, right? Yeah. So we're going to use the integrating factor method. This is linear ODE. Okay. So what you do is you multiply the sigma on both sides of this equation. okay, on both sides of this equation. Okay. All right, and to simplify my writing a little bit, I'm going to let tau equal to RC, okay, and the tau equal to RC. So I think you did an experiment. The reason we call it tau is because this is so-called what? Time constant, right? Time constant, okay? So then this equation here, just sigma 1 over tau, this is 1 over tau in here now. And to apply this integrating factor methods, we wanted to rewrite this side here into this, right? Into this. Okay. In order to do that, we have to let sigma prime equal to sigma multiplied by this, which is 1 over tau at here. Okay. So we have to have this relationship. And you solve this differential equation for a separating variable, and that sigma can be solved, which equal to e to the power 1 over tau t. Okay, so that sigma equal to this. So I'm kind of skipping one step here, but you just separate the variable, you'll be fine. All right? Yeah. Okay, so once I get my sigma now, okay, and I'm solving is sigma vc. Okay, this is d here, equal to sigma 1 over tau, okay, vst and dt, right? Basically, I'm solving this one here. Okay. Again, this if you divide the dt to this side, that's basically sigma c prime, right? Okay. Then you integrate. Okay, integrate. Okay, integrate. Okay, so this is where a little difference here now, right? In the all the previous example, when we do the integral, we just do the integral. Okay, and then if there's an initial condition, we apply the initial condition, right? Yeah. So the other way of solving initial condition problem, initial value problem is right at here when you do this integral. Okay, when you do this integral here, and instead of just do the integral, you integrate from 0 to t. Okay, integrate from 0 to t. Okay. So the reason is because from 0 is because, let's say the question gives you initial condition at the time equal to 0. Right? So let's say you know Vc of 0 equal to something. Okay? And we integrate to t, so we're interested in a general response at any time in the future beyond 0. Right? So that's why we integrate to t. Okay? So this is another way of solving initial value problem. Okay? Initial value problem. Okay, so now let's take a look at the if I do this, right, what's going to be, huh? That's going to be, bearing in mind, what's the sigma here? Sigma is this term, okay? Sigma is this term here, okay? Yeah. And this side here, it's just, I'll plug the sigma into this equation now, okay? Vc, and, right, 0 to t. Okay, that side is just this, right? That side is just this. So, Vc is a time function, right? Vc is a time function. So I guess when you do this, when you do this integral here, this sigma instead of using a t at here, right? Instead of using a t, when you do this integral, because you already have a t here, the dummy variable here, I guess to be less confusion, you can use another one that is u at here, right? As a u. I know this is probably a little confusing now. Yeah. Is that okay? Not okay, right? Yeah. Okay. So not okay. So let's write it again. So this is, see, I'm not writing here. I'm not writing this. I'm not writing this independent variable here, right? Yeah. But if I want to write my independent variable here, this integral is 0 to t, because I use a t already, right? Use a t already. So when you do this integral, this sigma here, I know my sigma is a function of t, right? But since I'm doing this integral with the limits of t here, instead of using a t at here, I change my dummy variable to u, or to something else. Okay, to something else. And the vc at here, same thing. I'll change that to a u. Okay, change that to u. I'm not really changing anything. I'm just changing this dummy variable just to cause less confusion. Okay, yeah. Because originally I don't have to do any change because what I had there is a indefinite integral. There's no limits there, right? There's no limits. Okay, yeah. So same thing on this side here. Same thing on this side here. So we're using t at here, right? Using a t here. So technically speaking, what you need to do is you need to change everything to u just to cause less confusions like that. Okay, just cause less confusions. Okay. So that's basically the little difference at here from the other examples. Okay, from the other examples. Okay, so now let's do this integral here. Let's do the integral. And this side of integral, still any questions? Yeah? Okay. So so this side, the results, it's just these functions, right? So just sigma u is this, VCU we don't know, so we're trying to solve. So this is 1 over tau u, and VCU. What do we do? Right, we have integral limits 0 to t, right? So that's this one, right? That's the left side. It's the left side. Okay. And the right side, okay. The right side, the problem is we don't know what the Vs, the input is, so I'll just leave it as it is, right? Yeah, we're trying to solve a general. But I can take the 1 over tau out of the integral, okay? And this is 0 to t. I'm plugging the sigma u at here. This is 1 over t tau and u, Vs, u, and du. Right? Okay, so that's this one here. All right, so let's do this. That right side, that left side here. Plugging the 0 and t into this one here. Plugging the t, it's 1 over tau t, Vct, right? Vct. Plugging the 0 into this exponential, which becomes 1, right? It becomes 1. So this just Vc 0, right? When you put a 0 here, Vc 0. Okay? Yeah. The other side, so let's leave it. Okay. If we have Vs, and we'll be able to solve that. Okay? But for the time being, just leave it the Vs of u there. Maybe I should say this. This is input, okay? This is input to the system. Okay, so now move this Vc naught to the right side. And move this to the right side and divide this e to the power of 1 over tau t, right? Okay, so let's see what happens. So Vct equal, when you divide this term here, this is a positive, which will become negative, right? It becomes negative. So that becomes negative 1 over tau t. And Vc naught plus e negative tau t 1 over tau 0 to t e negative tau u Vsu du. Okay. So you might wonder, what the hell are you doing here? This is getting so complicated. Well, just wait for a second here. I'll show you the results, which is actually interesting. Okay. Yeah. Just bear with me here. But is this okay? Right? From here to here. Yeah. So I skipped one step basically. The step I skipped it. Well, I said first step is to move this term to the right side here, right? Yeah. And then divide both sides by this coefficient. So when you divide both sides by this equation, this becomes 1, and when you divide this one here, 1 over that is negative, right? So I have this here for basically, right? Yeah. Okay. Okay. So one more step here. Okay, one more step. So you see, this is integral dominant variable with respect to u, right? With respect to u. And here is e to the power of 1 over tau t, right? So essentially, this quantity here, I can think of as a constant for this integral here, right? So I'm going to move this quantity into the integral, okay, into this integral, okay? So I'll show you what they look like now. So when I move this quantity into the integral, okay, so you see what happens, right? You got two exponential functions, right? So when you move this one here, basically means this multiplied by this. Does that make sense, right? And this multiplied by this means e to the power of this quantity plus this quantity. And that means basically 1 over tau, right? I'm gonna take out negative sign here, so negative 1 over tau and t minus u. Okay. And vs u du. Is that okay? Yeah. So 10 seconds, explain to your neighbor how this happens, eh? You know, it's just 8 o'clock, I think everybody's falling asleep here. Yeah. Good. Yeah, when I say explain to your neighbor, actually, I didn't mean to explain it. You can tell a joke, you know, whatever, just to wake yourself up. Okay, so anyway, what I did next is I didn't do anything except I just changed this position of the two functions. Okay, just two functions. Yes? There's a t in the first term. Oh, yes. Thank you. Okay, so now I stop writing. And I want you to observe this integral right here. Okay? What does that remind you? Somebody says? Convolution. Exactly, right? Convolution. Which one? Which one convoluting which one? Vs, well, I'm going to write back to the convolution now, right? So Vs t, convoluting which one? And t. So this convolute this one, right? Was that okay? This is basically the definition of convolution, isn't it, right? This definition convolution. Okay? Yeah. Okay. Now, let's just suppose that, what's this guy? This is the initial condition here, right? This is the initial condition. If Vc of 0 equal to 0, okay, if Vc of 0 equal to 0, then this basically means Vct equal to 1 over tau Vst convolute this guy here, right? Convolute this guy here. Okay? Yeah. And what is Vs of t? It's input, right? It's input. So input convoluting this function give you the output. And what does that remind you now? Somebody said it louder. Impulse response. So remember what the impulse, when we talk about the linear time invariant system, the impulse response, what did we say? We said, if I have the impulse response, and now I have a different input to the system, the corresponding output of the system is basically the new input convolute what? The impulse response, right? You see here, what's the, this is a general input, right? This is general input. You have any input convolute this one multiplied with scale, which is equal to this, right? Which is equal to this. So in other words, what is the impulse response of the system? If I give you this one here, what's the impulse response of the system? H of t equal to impulse response of the system is h of t equal to what? 1 over tau multiplied by this guy here, right? That's it, right? That's the impulse response of the system, okay? Impulse response. Oh, yeah. So you look at all the inherent things that are here, right? Look at the inherent things here. Any questions? Yeah, all good? Okay, now let's talk about specifically, right? Specifically, let's say, okay, if my input is a unit step input, if input VST is a unit step, let's say maybe not a unit step, maybe a scaled up unit step. Let's say AUT, right? AUT. And what will be the corresponding output VC, right? What will be the corresponding output VC? So what we can do is, here is a general solution here, right? This is a general solutions. All you need to do is replace this guy with what? A. So basically, you're going to replace this guy with this, right? So basically, VSU equal to AUU. Well, I guess, yeah, that's not good. But what you notice, you see the U changes from where to where? 0 to t, right? And you know the unit step function is 1 when t is greater than 0. So basically, you don't have to leave that u there. You can just change this one to a quantity of a, right? Quantity of a. So that means VCT equal to VC naught and e to the power negative 1 over tau t plus 1 over tau 0 to t and a e to the power n over tau t minus u du. Okay, so that's going to be the solution when the input is unit step function, and which is what we call unit step response, right? And this is integrable. You know, you can a here. This is just the exponential function. Remember, tau is a constant. Tau is RC, right? RC. So you can integrate this one for sure. And the result of the integral is VC naught and A1 minus this. Okay, 1 minus this. That's the result. Okay. If initial condition is 0, okay, so if VC naught is equal to 0, then VCT is basically A1 minus this. Okay, it's basically this. Now you look at this solution here and think about this response, right? Think about the response. And then think about, does that make sense or not, right? Does it make sense or not? So this is a negative, so exponential decay function, right? Which means as t goes to a bigger value, this quantity will go to approximately 0, right? 0. So the end results of this VC will be simply just the quantity of A there, right? So that's why you see the response is like this, decay, decay, like this, right? Like this. So however, you need to be careful though, huh? When you give your input to your system, which the input of system is square wave, this duration here, or the period here, and the half period, this duration in here has to be bigger enough in order to observe the settlement at here. That make sense? If you have let's say if you have a t maybe only 0.1 seconds, you probably you're going to see is up to here, and then it start to go down, right? You don't see the whole picture at here, right? Yeah. So that's how you need to be careful here. Yeah. Now, I think you learned this. Time constant tau, which is RC. Why is it called time constant? Because the time it takes to go up over here, which is 63% of this step change, and the corresponding time here, this is tau. Okay, this is tau here, right? It's tau here. Okay, yeah. All right, any questions? All good? Yeah. Okay, come here. Yeah. So class is over. Yeah. The midterm for the 246 will be up to this lecture, right? So basically up to the first order differential equation integrating factor methods. Okay. I'll confirm that when Through email too.
How does this u become a t, but this u became 0?
Oh, see, this is basically the definition of the convolution. See, when we write definition, let's say starting from here. Now, what do we do? If I use the definition as integral 0 to t, and then generally what I use is tau, right? But you know, I already have a tau here. So that tau is the constant RT. So in order to avoid confusion, I'm going to use a u. You see what I'm saying, right?
I think I get it.
Yeah. Come here. See, in general, convolution is this. Convolution is f of t convolute t of t is 0 to t f of tau t of t minus tau d tau, right?
Yeah.
And I don't have to use a tau here. I can use a u, right?
Yeah.
Okay. Right. So if you compare this one to what you have there, that's basically this quantity.
I get it.
Right?
Okay.
Yeah, I'm using u instead of tau here because I already have a tau there. Right?
Yeah. It makes sense.
Yeah.
Thank you.
Good. Yeah.
I have a question.
Just a second. Let me stop this guy.